In this video, I'd like to introduce some of the vocabulary that we're going to use starting in section 1.2 and for the rest of the course. We're not going to do any problems in this video. We're just going to get the vocabulary down, and we're going to leave the problems for class time. We'll work the problems together. So a zero row has all zero entries. A non-zero row has at least one non-zero entry. I have an example of a matrix here with various entries involved, and there's one zero row and four rows that are called non-zero rows. It's kind of a strange terminology because that last row has many zeros, but because they're not all zero, we call it a non-zero row, right? Non-zero means it's not all zeros. The leading entry of a row is the first non-zero entry as one moves from left to right. Here's another example of a matrix with leading entries marked. Actually, it's the same matrix as above. The first row has a leading entry of 2. The second row has a leading entry of 1. The third row has no leading entry, since all the entries are zeros. Fourth row has a leading entry of -1. And the fifth row has a leading entry of 4. We're going to learn about how to put matrices in row echelon form and reduced row echelon form. And here we spell out exactly what we mean by both of those forms. A matrix is in row echelon form if all zero rows are at the bottom. Number 2, if a leading entry of any row is to the right of the leading entries of all the rows above. And 3, entries in a column below a leading entry are all zero. Now that's quite a mouthful, and it's okay if you can't, I wouldn't get what all that meant just from reading those words. We're going to work some examples in class that will bring the 3 parts of this statement to life a little bit. There's another form we put a matrix in called reduced row echelon form. And so this is a little bit further along from the row echelon form up above. A matrix is in reduced row echelon form if, in addition to 1 through 3 above, we have 4, all leading entries are 1s, and 5, the column of any leading 1 has all zero entries other than 1. And again, you're like, what? I don't get what that means at all, and that's okay. We're going to come back to this as you'll be able to read back over this after we do some examples, and I think these 1, 2, 3, 4, 5 conditions will make a lot more sense at that point. One note I have here is that number 4 I often include in the row echelon form. So number 4, I think it's often easier to just include it in row echelon form. It's easier to put a matrix in row echelon form if we make all leading entries to be 1s. You'll notice I put the word row in parentheses for both of these. I always learned of these as row echelon form, reduced row echelon form. The word row is just in my soul here. Our textbook leaves out the word row and refers to these as echelon form and reduced echelon form. It means exactly the same thing whether you put the word row in there or not. In class, I'll always use the word row. That's just what I'm used to. A little bit more vocabulary or actually terminology from this section, 1.2. Our textbook refers to Theorem 1. Any matrix in is row equivalent to one and only one reduced row echelon matrix. What that means is if different people apply the reduced row echelon process to a matrix, they all end up with the same answer. That's not true for row echelon form. If different people apply row echelon form, they might end up with matrices that look slightly different, even if they started with the same. But the reduced form always comes out the same for all people. More vocabulary. Pivot. A pivot is the leading entry of a row that ends up being 1 in reduced form. And I think I put the arrow because there's something wrong with my grammar here, but the leading entry of a row where that entry ends up being 1 in reduced form. I put down a couple examples here for us to look at. These are the two matrices that we ended up with in the videos from section 1.1. The matrix that I'm pointing to here is the matrix we ended up with in the part 2 video. On the right is the matrix we ended up in the part 3 video. So I've marked the pivots in the first matrix. I put squares around the pivots. The pivots are the leading entry of a row that ends up being a 1 in reduced form. We even refer to them as pivots before we have obtained the ones. Pivot column is a column containing a pivot. So in these two matrices from the previous section, the first has 1, 2, 3, 4 pivot columns coming down containing the pivots. The fifth column is not a pivot column in that first matrix. In the second, there are 1, 2, 3 pivot columns, the first, second, and fourth. The third column of that matrix is not a pivot column. It does not contain a pivot. Gaussian elimination is the row reduction algorithm that we're learning. That's really, we started it in 1.1 without referring to it in that way. We're going to continue with examples now in 1.2. Gaussian elimination is named after a very famous mathematician from a couple hundred years ago whose name is Carl Gauss. He did all sorts of things, an incredible genius of his time. And our book also refers to Theorem 2 that I want to include on this sheet. And we'll only talk about the first part of it. A linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. And I want to go back to these examples again. The matrix that I'm pointing to on the left was from the part B, second video from 1.1. Remember, we obtained that matrix when we solved a system that had one solution, a unique solution. And notice that the rightmost column is not a pivot column. And that is therefore an indication that this is a matrix of a consistent system, a system that has a solution. And likewise, I guess, we could say on the right, this matrix was from the example from the third video of 1.1 where there was no solution to the system. And notice the rightmost column is a pivot column. So if the rightmost column is a pivot column, then we know for certain the matrix is attached to a system that is inconsistent, that has no solution. And for the statement about consistent systems here at the very bottom of this sheet, little number 1 and number 2, I'm not going to talk about those here. We'll talk about them when we finish the section, because we need to introduce the idea of free variables, something that we'll do in class together.